What if Wi-Fi could do more than just connect you to the internet? Imagine if it could tell you exactly where you are, even indoors, where GPS fails. Introducing our innovative Wi-Fi-based 3D indoor localization solution. Using signal strength data, 3D models, and advanced AI, we deliver precise indoor positioning like never before. Our system starts with a 3D model of the environment, Wi-Fi access point locations, and an RSSI vector, the signal strength captured by a device at a specific point. This data, our ray-tracing model creates a detailed 3D path loss map. This map simulates how Wi-Fi signals behave in your environment, considering walls, furniture, and other obstacles. This path loss map, combined with the RSSI vector, is fed into our 3D convolutional neural network. The AI processes the data to predict the exact location of the device in 3D space. The result is a precise location represented as a dot in the 3D environment, enabling pinpoint accuracy indoors. For wireless labs and Wi-Fi companies, our solution eliminates the cost and time associated with physical measurements. For the visually impaired, our solution provides precise indoor navigation, enabling safer and more seamless movement through offices, malls, and other indoor spaces. In retail, our system tracks customer movement patterns within stores. In robotic warehouses, our solution improves efficiency by enabling Wi-Fi-based localization and communication. Airports are vast indoor spaces where GPS falls short. Our solution leverages Wi-Fi to provide precise navigation to gates, shops, and amenities. Uniform seamless navigation across university campuses, indoors and outdoors, overcoming GPS limitations. Hold on to your popcorns. And welcome to Revolution Loc8.
Hope you have enjoyed our initial marketing video, and so Loc8, that's our product name. So sounds exciting, right? Loc8. So yeah, so have you faced this? You have seen this meme everywhere, right? Whenever you rely on GPS indoors, it obviously is going to mess up things, right? Because GPS doesn't work indoors. So that's the fundamental problem with GPS. But everywhere, when people think of localization, they only think of GPS. But that GPS doesn't work indoors. So that's a fundamental problem with GPS. So that's the thing that we push to change, right? So we have one technology in, at least, let us say, at least in nearly every home in America, which helps us to do localization, right? And it basically is the same type of technology as GPS, but just in a different spectrum. Guess what? It's Wi-Fi, right? So our product, Loc8, is purely based on Wi-Fi, right? It's completely based on Wi-Fi. It's a Wi-Fi based localization system that follows the same principle, same fundamental RF principles to design the subsystem as a whole, along with the use of ML. So that's the novelty in our project. We leveraged a particular technology called Wi-Fi fingerprinting, which essentially fingerprints every location with the received signal strength that it received from every access point. All right. The novelty in our approach. This is primarily an academic problem, a framework. This framework is primarily academic. It still has not been fruitioned out of industry. Okay. So this is primarily an academic framework, and that is why we wanted to focus on bringing this first to the market, Wi-Fi fingerprinting. So we essentially have an app that allows an user to send his RSSI fingerprint to a database, and that database would run a ML model, and that ML model would essentially send the fingerprint information to a central server, which we can use to visualize the position of a user, right? This can be used in several applications, which you might have seen in the video, in the introductory video. So Wi-Fi fingerprinting, the very novel approach about our fingerprinting idea is, we not only use this fingerprinting idea in isolation. We associate it with a 3D CNN model, which essentially takes a path loss image as input, and it will predict the position of a target given a RSSI fingerprint for any location. Okay, we our framework works only on indoor locations, on commercial indoor office locations, office or home locations. So we obviously cannot expect our model to work in outdoor environments, because it is not trained to be deployed in outdoor environments if there is no Wi-Fi presence. Okay, so that's the boundary of our toolkit. But obviously, this is Wi-Fi based, so it requires Wi-Fi. So it is Wi-Fi fingerprinting. So what is fingerprinting briefly? So generally, in simple words, generally a wireless RF signal, when it propagates through a channel, it experiences fading. Right, the received signal might vary considerably even at points that have very similar distance. That is a very fundamental point. So this can be a problem, because two locations with the same signal strength from two different access points might be identified as even though they might be two different points. Like if you take a single access point, right, and if you try to compare that access, if you try to compare a particular point's received signal strength from the access point to say another point, all right, in a circle every point would be of the same signal strength, because signal strength falls non-linearly over d squared. That's the free space path loss, right? So that is a fundamental problem. Two points that are situated radially at the same distance from an access point will have the same signal strength, right? So there is no spatial resolution, right? We exploit that by adding multiple access points, which are typically present in an indoor environment, right? There are multiple access points. Your smartphone hotspots can act as access points. So that's the primary winner uh, in our product. We use smartphones, their hotspots, to do localization, right? That GPS cannot achieve, because we do it indoors, right? So this can be actively exploited for high precision localization by the fingerprinting approach, right? So typically we fingerprint the RSSI vector from every access point, and we feed it to our pipeline. So let me just go through a brief descriptor of our pipeline. But before that, we first wanted to describe the models that we used for our measurement criteria, because whenever we start to deploy a product, we actually need to first do some research and some references for our product to be successful. So what are the references? Typically, generic wireless channels, they typically are generic wireless models. They can be approximated by 5 channel models. The first one is the free space path loss model, but this free space path loss model has the disadvantage that it does not work in a practical scenario, because free space path loss does not account for reflection loss, does not account for diffraction, all the other RF mechanisms that happen. It does not account all those factors. So that's the disadvantage with free space path loss. It is ideal, all right. So then we moved on to another path loss model called the Okamura Hata model, which is basically Okamura basically is a scientist who conducted several experiments in Japan, indoor experiments in Japan, to identify the received signal strength from different access points uh, in a very commercial indoor setting, right? And he statistically formulated an equation for how the path loss drops with the distance in a commercial indoor setting. So this is one another model that we exploited. The other models that we exploited are the 3GPP model. 3GPP model is the current standard 5G NR model, that is being utilized by the market. LTE as well as 5G both are standards developed by the 3GPP consortium, and this 3GPP's consortium's indoor propagation models are widely available in the internet. So we leveraged these models to act as a reference point for our pipeline. Next, we have the 802.11 model. Obviously, the 802.11, more popularly called as the IEEE 802.11 model, is basically the Wi-Fi consortium, right? So the Wi-Fi that we enjoy in our home is essentially developed by this consortium. So they proposed a particular path, indoor propagation model that can be used to simulate how the RF waves propagate in indoor environments. So that is one thing that we could be exploited, that we took advantage of, right, for reference. And the final model that we used is the ITU model, the International Telecommunication Union prescribed indoor propagation model, right? So everybody knows the ITU. So ITU proposed a model, indoor propagation model, that works in all types of indoor environments, office buildings, multiple floors. So, for example, it takes into account the diffraction, the refraction over multiple floors in a particular indoor environment. So there are a lot of aspects that obviously due to the concern of time, I would not like to go into much detail. But to beginners, to layman people, simply put, these are indoor propagation models that simulate a practical indoor environment as close as possible in an averaged manner, right? So we used these models to initially calibrate our approach, to calibrate the results that we got, right? So let me actually go share a Python code that I worked on initially for this calibration. So, for example, this is a simple Python code where we imported a lot of libraries, and this is called Wi-Fi fingerprinting. So, we simulated uh, a normal room, right? A three-dimensional room, and we set up access points positions, and we try to use ITU model here, just to showcase you, right? And we allocated all the important parameters, right? It's the transmit power, center frequency, all these floor penetration loss factor, all those technical parameters. And then finally we run this code to see how exactly a commercial indoor environment has a path loss map, a heat map, right? And so this is how it is. So for every access point, say this is the position of an access point, this is the position of an access point. For every access point, the more bright, the more darker it is, the more signal strength there is in a particular position. So here we can see a simple two-dimensional localization, two-dimensional path loss map, right? This is for every access point 1, access point 2, access point 3. And these signal patterns can be leveraged to finally map it to a point. You can very easily see here. So at every point, you can see the signal from a single access point varies, right? But you can also basically map out trajectories where the signal strength from an access point might be the same everywhere. You can basically imagine these radial cases, right? So these are a problem if you just use a single access point. That is the advantage that we are exploiting. So what we are doing is we are using multiple access points. So more than by bare minimum we need to use at least three. So that is what we used in this case. We simulated three access points, and the signal from all those three access points, they would be the probability that all the three would basically have duplicates would be very very minimal. So mathematically we are minimizing the probability that a particular location wouldn't be unique, okay? Which is the primary purpose of fingerprinting, which is the primary purpose of any localization, which is the uh, god given right to any localization, which we are leveraging, right? So that's it. And yes, okay. So let me go back to the presentation again. Right. So just to brief detour there, right? So these are the models that we used. Now coming to our pipeline, right? Before coming to our pipeline, first, uh, the very starting of our pipeline is first, um, the ideation phase. Okay, then we go to the development and deployment phase. So talking about the ideation phase consists of three simple steps. They look simple, but they are very intricate if you go into a individual block. So the first thing is, in the ideation phase, we have to first collect RSSI fingerprint using three smartphones. Why should we collect it? Because first, to build our ray tracing engine, we first had to initially, uh, okay, let me just briefly walk you through these steps. First, we collect the RSSI fingerprint, and then we build our ray tracing engine, and then finally we feed that ray traced path loss model to our ML model, which gets trained on these heat maps, and then finally we expect it to uh, predict the position of a target given a particular location, right? Okay, so that's the overall summary of our project. That's what we are doing. Okay, now coming to the individual block. So the collection of RSSI fingerprints, what is it doing? Let me navigate to this part, right? So here you can see this animation describing three smartphones placed around the corner of a house, and you can see a smartphone moving. So this smartphone you can imagine to be a normal target. Okay, so he is moving across this room, and you can see the received signal strength that he receives from every access point. He or she receives from a particular access point might vary. Okay, it would be a vector. Okay, that vector would be unique in such an extent that it would accurately, minutely differentiate every point. That's why we call it fingerprinting, because every x comma y or x comma z location would be unique, because it would be mapped to a unique RSSI vector. Okay, so that's the summary of what we are doing. That's the uh, inherent property that we are exploiting. And how is this advantageous compared to other conventional Wi-Fi, other conventional localization methods? You have time of arrival, you have difference time of arrival. These are very popular methods that are being leveraged in GPS. So why does we not utilize those methods? The disadvantage with those methods are they require highly synchronous clocks to work, right? That would be a big problem, and they would not work in non-line of sight scenarios, which is the primary case for practical scenarios. Okay, so uh, those disadvantages can be maneuvered by the use of Wi-Fi fingerprinting, because Wi-Fi fingerprinting, through its act of fingerprinting, it innately recognizes the very nature of the environment through the radio map, through the heat loss map. Okay, so that's the advantage that we are leveraging, right? So this is the ideation phase, the first phase of the ideation phase. The second phase is building a ray tracing engine. All right. So initially we built few simulational models that I walk through about. Those are used as references. For what? Those are used as references for us to ultimately build a ray tracing engine, right? Using Blender, MATLAB, and Python, right? A combination of all these three. Why do we want to build a ray tracing engine? The first reason is our ray tracing engine will not be generalized. It would give a particular heat loss map for every location that would be unique to that location. It is not generalized. Whereas the conventional simulational models that we use are generalized. They are averaged out for every indoor environment. So that is not good, right? Averaging is not good. Whereas the ray tracing engine that we built, which took us an enormous amount of time during the course of the entire project. So I briefly worked on the RF part as well as majorly on the ray tracing part, and my friend Sharvesh too, my other teammate Sharvesh too, worked majorly on this, and my other teammate Mayank worked majorly on the machine learning aspect of this. So generally in our to sum it up, in our project we can basically distinguish it into three modules. One is the data collection module, The second one is the ray tracing module. The third one is the machine learning module, right? Yeah. So this is the ideation phase. So we build the ray tracing engine using Blender, MATLAB, and Python, and then finally we built several ML models, which would be fed in, which would be fed the which would get basically the path loss map fed in, right? And just basically try to correlate between a particular environment and its path loss map, right? So we would basically, during the training phase, we basically feed the um, we basically feed to the ML model the 3D model, the OBJ file, as well as the heat path loss model, and the ML model learns to correlate between these two, right? And finally, for any given location, for any target RSSI vector, it predicts the XYZ. So that is the advantage that our ML model had, which Mayank is going to talk in detail. This was a very big phase, the ray tracing as well as the ML model phase, right? So let me move to the next slide, which is more about the development and deployment phase. So in the development and deployment phase, the first, this is basically our deployment phase, right? It walked through our complete prototype, right? So we first feed the 3D model of a desired target, okay, to which we are going to do the ray tracing to a ray tracing engine, and this ray tracing engine would finally uh, output a path loss map, which is given as a numpy file to our 3D CNN model along with the RSSI vector of the target. Okay. Now, this particular after this step, we would finally expect the ML model to output a 2D and 3D map, which we were able to visualize using Folium and Blender in the central server. Thus, the uh, precise position of a particular target has been pinpointed, and it has been visualized. So that is the overall outlook of what we did in this project, right? So yeah, so in the next slide, this is just a brief flow diagram about how the uh, about the ray tracing engine part. So basically, we have the 3D about the 3D model feeding in part. So we basically feed in the 3D model to our ray tracing engine, and this ray tracing engine basically outputs the path loss map, which would be fed to the model for its training, right? So in the next slide, yeah, this is just a visualization of how it goes through. So in the next slide, we have a simple flow diagram of the complete end-to-end pipeline. So this is our origin device, right? This is the target, and this target device would basically send its RSSI vector to our backend server, which we ran on AWS EC2, and this AWS EC2 runs our ML model, right? So this origin device collects the RSSI vector and it sends to the AWS model, which runs the ML model with with one additional input, which is the path loss map of that particular environment to which we have to test, to which we have to predict the position, target's position, and then finally this AWS server would finally outputs the device's coordinates to a centralized server, which is a laptop that we used for now. And in this laptop, we visualize the position of the target in 2D as well as in 3D. So that is the biggest advantage that we have. We show localization not only in 2D but also in 3D. So we pair our 2D coordinates with GPS so that it is absolute, right? So that's the biggest advantage with our project. So in the next video, we will have Sarvesh demonstrating the ray tracing module, and finally we would have Mayank demonstrating the ML module. Yeah. So here, as we can see, this is our measurement scenario, okay, which is one of the most important part. So this is the router, and here this is the steel frame, and this is a mobile phone whose hotspot is going to be turned on, and similarly there is another phone which I am holding, whose hotspot is also going to be turned on. We're just demonstrating that. And there would be another phone in the other side of the other corner of the room, whose hotspot would also be turned on. Now this is the test phone, which is this is the target. So this target is collecting all those signals, and it is once this button is pressed, the all those RSSI vector data would be logged on to the AWS EC2 instance remotely, and it would perform the prediction using its ML model, and finally it would output it to the central server. Okay. Thank you.
So here we can see that we are getting the data sent to our EC2 instance, and we are getting a response to our local server as well.
As an RF engineer at Virus, having a tool like the ray tracing model combined with a CNN-based prediction engine is honestly a game changer. It helps us predict the path loss map for any 3D location-based model before we even head out for the measurements. This means we can identify things like high loss areas or interference hotspots in advance without physically being on site. So it saves a lot of time and helps work more efficiently. For example, we can focus on key aspects like the setup placement, like the antenna placement, optimizing coverage, while testing different scenarios beforehand. This is especially useful in like more complex and tricky environments. So, like, complex indoor spaces or dense urban areas where small details can make like very big difference. So ultimately, it helps and lets us plan smarter, making better decisions and deliver stronger network designs without wasting resources.
Yeah. So this will be the very simple UI for our app, which will just send RSSI data, which will then be stored in our centralized server. Now we'll look into the server code that we have defined here. So here we have the server code which is defined in the EC2 instance. So we perform some pre-processing because at a given time, we know that we might get a lot of beacon signals. So we would like to reduce the number of points that are being handled at a given time and to always get the most recent RSSI vector data. So in this particular array, we would like to determine which SSIDs are necessary to perform the indoor localization. So we define those here and then we group them with respect to the timestamp. After doing it, we load our 3D model and then we use the predict route as a post method to predict our coordinates from the RSSI vector that we receive, which is received after pre-processing. So we perform some basic transformation operations to make the computation faster and we predict an output. So this then sent to our centralized server with the RSSI vector and the IMU values that we receive, sorry, the predicted values that we have received. Yeah, so this would conclude the server part in EC2. Now we'll go to the server part in our local system. Yes, so this is the server that we have defined within our system. Here we define the home coordinates, that is the coordinates from where we are making measurements. After doing that, we would also find the internal coordinates from the post request that we receive from our EC2 instance after the prediction. So we'll receive that and then we would plot these points in a folium map to show where these points are exactly located at. We'll do that, and then we'll plot a marker for the reference point and the predicted point that we have found out. So this will be shown in 2D, and the visualize predictions function that we've defined here takes in the RSSI vector data that we have sent to EC2, and it will also plot a identifier within the 3D model to find out where the object is exactly, so that we can visualize this in 3D. So to save the map that we found out for the 2D coordinate, we have also saved the map with the same folium functions, and we return the status code. Now we'll get into the 3D model part of identifying the object within the 3D model. So here we create a small colored sphere to denote the location of the object. So here we take in the object file that we have. So initially we pass the numpy file and the RSSI vector to get the prediction, but we have the object file with ourselves. So we would like to use the same object file, but plot the exact location of the target within the same object file and store it in a different file, that is a new file. So we create the colored mesh and then append it here, that is concatenate it here. Yeah, and then the predictions are visualized here. So this concludes the complete code part of the project. So we start off with the 3D model, we perform ray tracing, we get the numpy array and the RSSI vector. The numpy array and the RSSI vector are sent to our 3D model. The 3D model performs predictions on it and then returns the XYZ coordinates. These coordinates are used to do two kinds of identification, one with respect to 2 dimensions and the other with respect to 3 dimensions. To perform the visualization using 2 dimensions, we use folium, and to perform the visualization in 3 dimensions, we use the object file of the 3D model and then change the object orientations and the number of objects present inside the model to show it in Blender. Yeah, so that concludes the code part of it. We'll proceed with the demo.
Yeah. So now we'll look into the output part of the demonstration. So here we have the 2D map that is being plotted. So in this map, we can see that we have the origin location, that is P111230 here in LA. So the origin location of the house is being taken, and then the internal point which is being predicted is shown here. So in the same code base, you can also see that we have a proper response. We have hosted the web page and we have hosted the server in Grok. We have got proper responses, and then our faces are exported, and then we create an updated OBJ to visualize the room in 3D as well.
So, hello everyone, this is machine learning part. So before going to the machine learning model building, I'll go to the dataset which we manually collected. So we had a receiver X, Y and Z value and their corresponding RSSI XYZ value. So we manually collected more than 100,000 dataset. These all are collected manually. Now I'll go to the machine learning part. So at first I imported all the necessary libraries which are required for the model building, and after that I made a function which loads and pre-processes the dataset. So before loading and pre-processing the dataset, I do some exploratory data analysis. So at first I imported the dataset as a in dataset variable, and this was the first 5 values which we get using head. This was the shape which we got. We have 125,000 columns and rows and 6 columns, sorry, my bad. So after that I did some exploratory data analysis. So first I pair plotted all the data point to see how it is, how one point of the data set is according to the corresponding other points of the data points. So as you can see, the receiver X and RSSI Z, the corresponding nature of the graph is like this. After that, I made a heat map to get the correlation values which each of the corresponding columns, and then this was our plot. So I made a 3D graph just to properly visualize whatever we plotted. So if I zoom in a bit, you can see we have collected more than 100,000 data points at every single corner of the room. So after that, I plotted some line graph, which was RSSI versus receiver Z values. Then I did some histogram plotting to get a better insight of the data set. Then I made a variant plot just to get a better insight. Then a box plot and see there are some outliers in the data set. Then I created the model. For model building, I used TensorFlow API, and so this model structure was after a lot of tries and testing. We tried different type of model structures, model architectures, and different things. So finally, we found that this model architecture was the best for us. So it has a total of 18,051 uh, param parameters. Out of them, 17,539 are trainable and 512 were non-trainable parameters. Then, to get a better model building, I use callbacks. So I stop whenever the validation is constantly decreasing, and I put the patience as 20. Then after that, I made a checkpoint which will create the best model uh, every step. So and I check the monitor as validation loss and save the best one only. So this will give us the best model uh, for during the training process. Then I trained it for 200 epoch and made a 32 as a batch size. Callback being the early stop in and model checkpoint. So this was the plotting thing which I made. I'll show you the graph later. And then I made a main function in which I first load and preprocess all the dataset. Then we split the dataset into 80-20, which was 80% was given to the training and 20% for testing. Then I trained the model and then evaluated the model time and then plotted the model. And after that, I dumped all the scalars input and output, which can be used during the prediction of the values. So after that, I made a function named as make prediction, which will help us to predict the values. Then I trained the model, and the model was trained for 57 epoch. So we got an accuracy of 82.2%, with the loss being 11.06, mean square error being 24.43, and validation accuracy being 93.47. So as you can see, this was a really very good model. The test mean error, absolute error, we got as 14.48 approximately. And after that, I tested the model with some data set, data points to get the x, y, and z predicted x, y, z coordinates. So I feed in this values and I got this. And after that, I plotted that point in a 3D vector. So as you can see that this is the point which we got, which is the x, y, and z predicted coordinate. So this was the our graph for model loss, model mean absolute error, and model accuracy, which we got. And this was our model accuracy with every epoch. So as you can see, we had a very consistent model accuracy going on. So yeah, that's it from model machine learning part.
So we provide localization as a service in which we do a lot of intricacies such as data simulation, in which we simulate the environment to collect in-person data for indexing locals with global coordinates. And we made a ray tracing model, and we gave a very high weightage to the type of material present inside the environment of interest. We did object localization, in which we identify the network connected with object and target location within the enclosed structure. So size of market we divide into three parts. The first one is serviceable obtainable market, which has a market cap of $1.8 billion. Another one is serviceable addressable market, which has a market size of $6.3 billion. And the overall is a total addressable market, which has a market size of $12.5 billion. So we are currently targeting the 5 to 7% of the total market, which translate approximately to 90 to $126 million. And it has a huge growth potential of approximately 22.4% CARG over time. So we do have two direct competitors. The first one is Idaho, which works on Wi-Fi optimizer, and it has a dedicated device, and it works with Wi-Fi signaling, and it is extremely expensive to operate. Plus, it requires an additional device to operate. So we are better from them because we don't need any. We works on existing architecture, and we don't need any dedicated device extra from whatever we have. The other one is Skyhook, which works on cellular and Wi-Fi data. Even though it sounds better than us, but it's extremely expensive, and our model is definitely cheaper than what they provide. So these are key competitive advantages. The first one is the cheaper equipment, since we are using the existing architecture infrastructure which is present. So our basically we don't need any external uh, devices to obtain whatever we are doing. We are extremely customer focused, and we have a very cutting edge technology in which we use latest tools and technology to stay ahead from our competitors. So we do have a revenue model which we planned. The first one is a basic one, which start with $30 per month, standard with $35 per month, and premium with a $40 per month. So these all are the advantages, features which we are planned to give with every premium models. So we consist of three members: the Vikram Vasudevan, me Mayank Srivastava, and Sarvesh Shankar. These are the references which we referred during our making of the project. And thank you.